Scientifically proving the existence of more than three dimensions is a complex and highly theoretical endeavor. While we can easily observe and experience the three spatial dimensions, length, width, and height, and the fourth dimension, time, through the framework of space-time in Einstein's theory of relativity, proving the existence of additional dimensions requires indirect methods. These dimensions are typically thought to be hidden or compactified. Here are some of the scientific approaches used to explore the possibility of more than three spatial dimensions. One of the most prominent theories suggesting the existence of more than three dimensions is string theory. String theory posits that the fundamental particles we observe, such as electrons and quarks, are not point-like particles but rather tiny vibrating strings. These strings can only exist and vibrate in a universe with more than three spatial dimensions, typically 10 or 11 dimensions in different versions of the theory. In these models, the extra dimensions are thought to be compactified, meaning they are curled up so small, at scales close to the Planck length, around 10 to the minus 35 meters, that they are imperceptible to our everyday experiences. Scientific approach indirect evidence via particle physics. One potential way to detect extra dimensions would be through experiments at high-energy particle colliders like the Large Hadron Collider. If extra dimensions exist, they could influence the behavior of particles at extremely high energies, possibly leading to the production of Kaluza-Klein particles or other phenomena predicted by theories with extra dimensions. Theoretical models based on Einstein's general relativity, such as the Randall-Sundrum model, also propose extra dimensions. In these models, our observable universe is a brane, a three-dimensional membrane, floating in a higher dimensional space. In these theories, gravity might propagate through the extra dimensions, while other forces, electromagnetic, strong nuclear, weak nuclear, remain confined to our three-dimensional brane. This could explain why gravity appears weaker than other fundamental forces. It spreads out over more dimensions. Scientific approach. Gravity at small scales. Experiments designed to test the behavior of gravity at very small distances, typically in the micrometer range, might detect deviations from the inverse square law of gravity, which would be an indication of extra dimensions. Current experiments haven't found such deviations, but future, more sensitive tests could provide evidence. Some cosmological models, especially those based on inflationary theory or the idea of a multiverse, suggest that our universe might be just one of many in a higher dimensional space. These models don't directly prove the existence of extra dimensions, but they offer frameworks where extra dimensions could exist. Scientific approach, cosmic microwave background. Subtle patterns in the cosmic microwave background, which is the afterglow of the Big Bang, could offer clues about the existence of extra dimensions. For example, certain anomalies in the CMB might be explained by the influence of extra dimensions during the early universe. Though we haven't directly observed extra dimensions, much of the mathematical consistency of modern theoretical physics, like string theory, relies on the existence of extra dimensions. These dimensions allow for the unification of the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. Scientists use highly complex mathematics to model how the universe would behave if extra dimensions exist. These predictions guide experiments such as those conducted in particle accelerators or gravitational wave observatories to search for indirect evidence of these dimensions. Gravitational waves, ripples in spacetime caused by massive objects accelerating like black hole mergers, might provide indirect evidence for extra dimensions. If extra dimensions exist, the behavior of gravitational waves could differ from what is predicted by general relativity in a four-dimensional spacetime, which includes three spatial dimensions plus time. Future detections of gravitational waves, especially with greater precision, might reveal slight anomalies or additional energy loss into higher dimensions, providing evidence that extra dimensions exist. Black holes are regions where gravity becomes extremely strong, and studying them can give clues about the nature of spacetime, including the possible existence of extra dimensions. Some models of extra dimensions predict that small black holes, if created in high-energy collisions, would evaporate differently due to the presence of extra dimensions. Observing this behavior in particle accelerators or through astronomical observations could provide indirect proof. Currently, the existence of more than 3 spatial dimensions is a theoretical idea, with many models such as string theory and brane world models relying on their existence to solve complex problems in physics. However, direct experimental evidence is still lacking, and scientists are actively working on high-energy particle collisions, gravitational wave measurements, and tests of gravity at small scales to potentially reveal these hidden dimensions. The proof, if it comes, will likely be indirect, relying on subtle deviations from known physical laws that point to extra dimensions beyond our intuitive experience of the universe.